Okay, now we get to chapter 3, where we talk about chemical reactions and stoichiometry. You might wonder, where is that term stoichiometry? You probably encountered it in high school chemistry, and you may have some sense of it, perhaps not an enjoyable remembrance. But you may also wonder, where does it come from, and what exactly does it mean? Well, the term stoichiometry comes from a law that was postulated in the mid-1700s. This is the law of conservation of mass. This was postulated by a French chemist, Antoine Lavoisier, who is considered to be one of the fathers of modern chemistry because of his careful experimentation with chemical reactions and his quantitative measurements. And Antoine Lavoisier wrote that nothing is created during a chemical reaction, that you have an equal quantity of matter existing before and after the experiment. Now, Lavoisier might have made many more contributions to the field of chemistry, but unfortunately his life was cut short during the French Revolution, as he was guillotined during the Reign of Terror. But shortly after his death, in the early 1800s, you'll remember that John Dalton came along, and Dalton took Lavoisier's law of conservation of mass and wrote it as one of his postulates for atomic theory, stating that atoms are neither created nor destroyed during a chemical reaction. Okay, so how does this relate back to stoichiometry? Well, stoichiometry is our way of making sure that the law of conservation of mass is upheld. It's our way of keeping track of atoms in a reaction to make sure that we have the same number of atoms before a chemical reaction and after a chemical reaction. So let's look in this in a little bit more detail. And first, we'll introduce just the chemical equation itself. So all chemical equations look something like this example shown here. We'll have some materials on the left side, and then we have a reaction arrow, which always points to the right. Now, later on, you may see a case where there are two arrows, one pointing to the right and one pointing to the left. You'll get to this in general chemistry too when we talk about equilibrium. But for our purposes right now, we'll draw only one arrow pointing to the right. And then on the right side, there's again some material present. Now, we classify the materials on the left as being the reactants. That's what goes into the reaction, or that's what we have at the beginning. And then the materials on the right, we classify as products. That's what we end up with after the chemical reaction. And the arrow simply signifies that a reaction is occurring. Now, we can write this in cartoon fashion, and this allows us to actually see a little bit more the number of atoms that are present. And the white atoms, white balls here are the hydrogen, red is oxygen, and you can see that a change has occurred. But additionally, we have these numbers in the chemical equation that come before the atomic symbols. And these are known as coefficients. Coefficients tell you how many of that type of molecule or atom are present. So it's not two just hydrogen atoms, it's two of this whole H2. Well, what does the H2 mean? Subscripts indicate the number of atoms that are present in that molecule. So here the 2 indicates that I have 2 hydrogen atoms present in the molecule as shown below. And then the 2 that comes in front, the coefficient, tells me that I have 2 of those molecules. So I have 2 H2 molecules. In front of oxygen, I don't have a number, so it's just assumed to be 1. And so there's a subscript here for 2, so there's 2 oxygen atoms, and so I have simply 1 oxygen molecule. We'll remember oxygen and hydrogen are members of our diatomic series. On the right side, we have a whole molecule that has H2O, of course water, we're fairly familiar with that. But this subscript tells me that I have 2 hydrogen atoms present and 1 oxygen atom, since it does not have a subscript. And then the 2 that comes in front, the coefficient, tells me I have 2 of those water molecules. So the total number of atoms in a molecule, or the total number of atoms present, are just the coefficient times the subscript. So I have 4 hydrogen atoms present on the left side, and I have 4 hydrogen atoms present on the right side. And I have 2 oxygen atoms present on the left side and 2 oxygen atoms present on the right side. On the left side, my coefficient is 1, but my subscript is 2. On the right side, my coefficient is 2, my subscript is just 1 in this case. Now, in order to follow the law of conservation of mass, we must have a balanced chemical equation. You've probably heard that quite a bit. What does a balanced chemical equation mean? It simply means that I have an equal number of atoms of each element on both sides of the chemical equation, on both sides of the reaction arrow. Now, to balance chemical equations, often we'll be given a chemical equation that's not balanced, and we need to change the coefficients in order to balance it. And there are very specific rules in terms of how we write a balanced chemical equation. And so first, and most important, is that we never, ever change the subscripts. If I have reactants listed and I have products listed, I never change the subscripts when I am balancing the chemical equation. And the reason for that is that changing the subscript changes the identity and the properties of the molecule. So if I had H2O, for example, if I changed the subscript and made it to be H2O2, now I've gone from water to hydrogen peroxide. Water we need for life. Hydrogen peroxide was toxic and would kill us if we just drank straight hydrogen peroxide. Of course, we'd also be in great danger of blowing up if it was truly pure hydrogen peroxide. Don't worry, the hydrogen peroxide you buy from the store is only about 3% hydrogen peroxide. It's not hazardous in terms of explosiveness. But pure hydrogen peroxide has very different properties from pure water. And so what we do, rather than changing the subscripts, we change the coefficient, and that changes the amount. And that allows me then to balance the number of atoms, but I never, ever change the subscripts. The second process for this is that I'll list the elements with the quantity of them that appear on both sides of the equation. And I'll go through an example here in a moment. And this helps us to know, okay, how many do we have at the beginning, how many do we have at the end, and what changes do I need to make in order to bring those two together? Now, my process of doing that is after I've listed what's on the reactant side and what's on the product side, then I will start with the element that appears in the least number of formulas on both sides. That way, if I change a coefficient for it, I'm not having to change multiple coefficients all over the place. I can just start with the element that appears in the least number of formulas, fix that one first, and then slowly work to the other ones. Now, first I'll change the coefficients to make them balance. And then next, I'll move on to the next least occurring element and change those coefficients to balance it. And finally, I will continue until all of the elements are balanced. Now, what does this look like practically? Let's go through an example. So I'm given some equation here. We have methane, which is CH4, reacting with oxygen to form carbon dioxide and water. And I have the reactants are on the left side of my arrow, then I have my reaction arrow, and then I have my products on the right side of the arrow. But if I first look through here, and if I list all of the elements on the reactant side and on the product side, it will look something like this. First, I list reactants and products, and then I list the elemental symbol and the amount of that element that are present. So on the left side, I have 1 carbon, I have 4 hydrogens, and I have 2 oxygens. On the product side, I have 1 carbon, I have 2 hydrogens, and I have 3 oxygens. So that gets me a starting place, and it helps me to keep track of what is present. The second step, start with the least abundant, the element that appears in the least number of formulas. You can look at this and say, well, carbon appears only in 2 formulas, one on the left, one on the right. Hydrogen appears only in 2 formulas, so I could start with either of those 2. However, I would not want to start with oxygen because oxygen appears in 3 different formulas. I want to start with the element that appears in the least number of formulas. In this case, I'll start with carbon. So I start with carbon and look and see what's on the left, what's on the right, and what do I need to do to balance carbon. Well, it turns out that carbon's actually already balanced. There's one carbon on the left, one carbon on the right, so I don't have to change that one. So I'll move on to hydrogen. This is the next element that also appears only in 2 formulas. So if I look at hydrogen, there's 4 on the left, but only 2 on the right. So I will change the coefficient on the right to fix the number of hydrogens on the right so that it matches the number of hydrogens on the left. Now I have 4 hydrogens on the right side because I have put 2 in front, and the total number of atoms is the coefficient times the subscript. And so I now have 4 hydrogen atoms on the left, which now matches the 4 hydrogen atoms on the right. So I look at my reactants and products, and I see that carbon's balanced, hydrogen's balanced. Now I move on finally to oxygen. And so if I move on to oxygen, what I will see is that now I had just 2 on the left and before, but I had 4 on the right, so I will balance it by placing a 2 in front of the oxygen on the left. Now I have 1 carbon, 4 hydrogens on the left side and 4 hydrogens on the right. And now I have 4 oxygens on the right, on the left, coefficient times subscript. And on the right, I have 2 from CO2 and 2 from the 2 water molecules. That gets me 4 oxygens on the right, and my chemical formula is now balanced. And so that is the process. And I would ask you to follow this very specific process. It will not lead you astray when you are going through and trying to solve chemical formulas and balance chemical equations. Let's go through a few more examples, maybe even a few more complicated cases. So let's just take this case. We've got carbon monoxide reacting with oxygen to form carbon dioxide. First, list the elements on both sides. That gives me 1 carbon and 3 oxygens on the left, 1 carbon and 2 oxygens on the right. And so then first, I can go through and say, well, carbon is already balanced. The only thing that is not balanced is oxygen. And I have 3 on the left and 2 on the right. What I will need to do in order to balance oxygen is I will have to change coefficients on both sides of the equation. What I'll note is that on the right side, CO2, no matter what coefficient I put in front of it, I will always have an even number of oxygens. Whereas on the left, I have a molecule, CO, carbon monoxide, that has only 1 oxygen atom in front of it. And so depending if I have an odd coefficient, I will have an odd number of atoms. So what I will need to have in order for these to be balanced is I will need to have an even coefficient in front of carbon monoxide. And then that will now allow me to make sure that I balance the number of oxygens on the left and on the right. So what I can do is put a 2 in front of carbon monoxide. That would now put me with 4 oxygen atoms on the left, and that only leaves me with 2 on the right, so I have to place a 2 coefficient in front of carbon dioxide, and this will now get me 4 oxygens on the left, 4 oxygens on the right. And now I'll just go back and double check to make sure that carbon is still balanced, and it turns out the carbon is still balanced in this case. Let's do another example with, again, still just carbon, hydrogen, and oxygen elements, but a slightly larger molecule, C5H10O2, plus oxygen going to carbon dioxide and water. Again, this is just a combustion reaction, which we'll talk about later. First step is list all of the elements on both sides. So here's my chemical formula again. Here are the reactants. On the left side, I have 5 carbons. I have 10 hydrogens. I have 2 oxygens from that molecule and 2 from this one, so I have 4 oxygens, whereas on the right, I have only 1 carbon, 2 hydrogens, and 3 oxygens. So I start with the element that appears in the least number of formulas. In this case, carbon and hydrogen both appear only in one formula on each side, but I'll start with carbon. To balance that, I simply need to place, I can do this a couple different ways. I could simply put a 5 in front of the carbon on the right side. Or if need be, I can put a 2 in front of the one on the left and a 10 in front of the carbon on the right. That will also work. I could also just start with the 5. And I will need to pause here because, yes,